Hey guys, this is Matt, and I'm back with another Masters tutorial, where today I'm going to be talking about maze generation. So let's take a look at a maze. So these are very simple mazes, kind of like corridors and big rooms. Very generic kind of walls and hallways. Maybe something that you could use for a dungeon crawling type game, or something similar to that. But there are two ways that you can actually change the environment and the types of maze that are generated, and that is with the gap and the number of doors. So let's change that gap. Let's put it down to say a 10, or let's put it up to 10, and then we're going to generate a new maze. So this really made it a lot simpler. You can see the path is a lot more diagonal, and the rooms are huge. So that's what the gap does. It increases the distance between these walls. Then you can also do something like put it down to 0 and make a new maze. And now it's all the walls are really close together. It kind of looks just like noise. So this probably wouldn't be too useful, but it does make it a bit more difficult for the algorithm. It has to go in a non-diagonal distance, so it makes a longer path. So I find that 5 is pretty good, so we'll put it back there. And now let's take a look. Well, let's generate a maze, and then let's take a look at what the number of doors does. So you see these little entryway. This is a door, here's a door, there's another door, just like that. So those are the doors. So if we make more, say 5, then let's generate a new maze. Now you can see there are a lot more gaps. So it just increases the number of doors that are on each segment of wall. And you'll see how the maze generation works. So each one of those doors is actually being created in 4 different places, technically. So that's a brief overview of the ways that you can change this map. Now let's take a look at some code. Here's the method that makes the walls for our maze. And this is a recursive method, meaning that it calls itself multiple times. And in order to get this method kick-started, you have to send it the smallest and largest x and z indices into the 2-dimensional array that represents the grid that you're trying to visualize. And in our case, it's going to be this nodes array here. And if you take a look at my previous videos, you'll find out how this array was created and what it's populated with. But after that, so after you call it, you're going to first come across this exit case. So if this is true, then the recursion stops, or at least this branch of the recursion stops, and it terminates. So it doesn't continue past this point. If the smallest x value is larger than the biggest x value minus 1 minus that gap, or if the smallest z value is greater than the largest z value minus 1 minus that gap. And this is why that gap was controlling the size of the corridors, because of the exit case here. So after our exit case is whenever we actually make the walls. So first we make the x wall. The first thing that we do is we make a random x value, and after that we go through all of the nodes from z small to z big. So all of the nodes that are in our quadrant. And we set the walkable to false. So we basically make them a wall. And now we're going to do the same thing for the z-axis. We're going to get a random z value from z small to z big. Now we're going to go through all of the x values from x small to x big, and using that random z value, we're going to set the walkable to false. Now we have basically 4 quadrants of nodes, and we need to connect them to each other by using the doorways. So we're going to use num doors, and this is a loop. And each one of these is basically taking one segment of wall. So there are 4 segments of wall, and we're going to take each one and we're going to put a doorway inside of each segment. And we're going to do that number of doors times. So if it's 1, then 4 doorways are going to be created. If it's 2, then 8 doorways are going to be created, and so on. And after that, we're going to do the recursion right here. So we're going to do one of the quadrants, so the smallest x, to the random x value minus 1, to the smallest z, to the random z minus 1, and so on. And I actually have a paint diagram that will probably make this a little bit easier to understand. So the 4 variables that we're keeping track of are x and z, and we need the min and the max. So the minimum value needs to be 0 whenever you start, and the maximum value is going to be 14. So it's size minus 1, since we're dealing with indexes. Size in this case would be 15. So 0, 14, and 0, 14. Now, according to our algorithm, we're going to get our random values. So let's just get both of them. We're going to get a random x, and let's just say it's going to be 5, and we're going to get a random z, which is going to be 9. Now, we go to that random x value, which is 5, and we're going to go through all of the z values. So, there. And now we go to the random z value, which is 9, and then go through all the x's. Alright, so this is the coordinate system that I was talking about. You have a coordinate 1, 2, 3, and 4, or quadrant, I mean, sorry. And after that, we created our doorways. So this is one segment of wall, the second segment, third, and fourth segment. And we're just going to place these randomly. Doesn't really matter where. Alright, so now we have a fully connected map. And this is where the recursion comes into play. So let's take the first quadrant as an example. In order to call this algorithm again, you need to give it the smallest x value, which is 6. So it's actually going to be the random x value plus 1. And now you need to give it the largest x value, which is going to be what was given to the algorithm. In this case, it was given a 14. And now you do the same thing for the z portion. You need the smallest z value, which is actually what was given to the algorithm, which is 0. And then you need to get the largest z value for this quadrant, which is going to be the random z value minus 1, so it's 8. And then you do the similar things for the other 3 quadrants. And I'm not going to continue that algorithm, but you end up getting mazes that look like this. Very similar to what we started here. Alright, that's about it. That is the end of this pathfinding series. Like I said, this was a project that I did for school. I'm going to be posting the paper that I read this from and implemented the algorithm of. This program and others are on our site, so you can take a look at that. We also have a GitHub account where you can go and you can download this code and you can play with it yourself and just take a look at some of the things that maybe you didn't quite understand. Alright, thanks guys.